Alright, this is the last video for Chapter 8. We are on Section 8.4, and we're doing the logarithmic and exponential equations Part 2. Now, for the last section, or I guess last day, we learned how to solve these logarithmic equations. Today I want to show you how to solve exponential functions. Now, you might be thinking, hey, we did this already in Chapter 7, in Section 7.3, and I'm going to say, you bet we did. But I'm going to show you another way of doing this, and this way that I'm going to show you today works for all different types of exponential equations. The ones that only worked in Chapter 7 were ones where you could actually rewrite terms with proper exponentials. So I want to just try to do a question that we've done in Section 7.3 first, and then I'm going to show you how to solve it using what you can do with what you learned last day. Alright? Got a special guest here today with me. My little daughter is with me right now doing this video, so she's touching the screen and trying to grab at the pen. So if you hear her scream, say hi. Okay? Alright, so the first one here, solving using exponentials. Remember what we did last time? Oh yeah, remember how we wanted to change everything to the same base? So remember 16 can be written as 2 to the power of, I think, 4? Yeah, so when you do it like that, you get 2 to the power of 3x minus 2, that's the same on the left side, but the right side, that 16 becomes now 2 to the power of 4. And remember, when you have exponent with exponent, you can then just multiply them together. So I'm going to distribute them. 4 times 2x is 8x. 4 times 1 is 4. And then you've got on the left side 2 to the power of 3x minus 2 still. And then what do we do before in Chapter 7.3? Once we found that the bases are the same, you want to just equate the exponents. So we made the exponents equal to each other. So therefore 3x minus 2 is equal to 8x plus 4. And then here we just do some algebra. So we will subtract 3x on both sides. So that becomes 5x on the right hand side. And then we'll subtract 4 on both sides, so you get minus 6. And then when you solve, you just nicely divide both sides by 5. You get the fraction negative 6 over 5. Pretty straightforward, right? Cool. Now, before I show you how to do this using logarithms, I want you to just review from last day that we had this little piece of information. Given that we have a base that's c, and the L and the R. L stands for the left side, R stands for the right side. All these things being bigger than 0. And of course, the C value can't be equal to 1. What we learned last day was if we have log base CL equals to log base CR, then of course the left side L equals to R. Well, what about vice versa? If I had L equals to R, then what I want you to understand today is if I take the log of any base of the left side, well, that's, of course, equal to the log of any base of the right side. Okay? What's the best base to use? Well, any one is fine, but because our calculator is in base 10, I would always ask you to take logs with base 10. Alright? So, with that knowledge in mind, I'm going to ask you to go back and do the same question using logarithms. Okay? So, I've got the left side, I've got the right side. So when I solve using logarithms, what I'd like you to do is take the log on both sides. And I'm going to use log base 10. So log 2 to the power of 3x minus 2 equals to log 16 to the power of 2x plus 1. And then now we have to use our log rules to help us solve this question. What are my log rules? Well, I've got exponents. So what can I do with the exponents? Yes, by the power law, I'm going to bring the exponents down. So I'm going to bring the 3x minus 2 down. So it's 3x minus 2. I'm going to put a bracket around that because I want you to understand that that whole thing is multiplied by log base, or not, log 2, sorry. It's log 2. Going to do the same thing with the 2x plus 1. Going to bring that down, and that whole thing is multiplied by log of 16. Okay? And so now, to solve this, remember log 2 and log 16 are just numbers. So now I've got numbers times the expression 3x minus 2. Well, let's just distribute. I'm going to go 3x times log 2, and that just becomes 3 log 2, and then x. Okay, so I want you to understand that whole thing is the number. And you have minus 2 log 2. Okay, that's the left side. Can you try to expand out the right side, please? And if you did 2 log 16, that whole number times x, and then plus log 16, I like that. Okay. Now, remember, you are trying to do algebra here. You're trying to just solve for x. So when you're solving for x, what you want to do is have all the things with x on one side. So you see how I have two terms here with x? There's an x and there's an x. So let's move them all to one side. So I'll keep the 3 log 2 on the left. I'm going to ask you to move the 2 log 16, onto the right. Okay, and then similarly with the other things, I'm going to move all those, the numbers, okay, to the side. Ooh, yes, you like the numbers too, don't you? Yeah, okay. And then now, what you're trying to do is you're trying to solve for x. So very simply now, if I wanted to just do this by solving x, notice on the left side, I've got x's on both sides. Why don't you factor that out? So I will ask you to factor out the x, and what you're left over with is just 3 log 2 minus 2 log 16. And once again, that's just a number. Okay. Well, how do I solve for x now? Well, you just want to isolate x by itself. So I'm going to ask you to divide both sides by that thing next to the x. So we'll have log 16 plus 2 log 2 all over 3 log 2 minus 2 log 16. And now I'm going to ask you to go use your calculator and actually just plug this into your calculator, and let's see what answer we get for x. To do that, let's please put a bracket around the numerator. So log 16 plus 2 log 2. Close the bracket, that's the numerator, divided by, open the bracket for the denominator, 3 log 2 minus 2 log 16. Close the bracket for the denominator, press enter, and oops, what did I do wrong? Yes, I know. And my daughter says I did something wrong. Well, where's my mistake? I think it's here. I forgot, or I put in an extra bracket. Let me delete that. I'll press enter now, and lo and behold, you get x equals to negative 1.2. Which is, of course, the same thing as if I change it to a fraction. Math fraction, negative 6 over 5. Okay. Now notice I didn't do any simplification in the logs here. I could have actually rewritten this nicer if I want to combine things together, but you know what? I'm solving anyways. I'm going to plug it into the calculator. Why bother? So I just left it in that form, plugged in the calculator, get the answer. Now this logarithm way is good because I don't need to know all the different types of exponents. I don't need to know that 16 equals 2 to the power 4, and I can still get this done. Yes, it might look a little bit more messy, but nonetheless, it's a foolproof way. So with example number 1 now, what I'd like to do is ask you to solve each of the following exponential equations now, but this time, let's use logarithms to help us out. Alright, so let's take a look. Well, you can take log on both sides in this case. So if I take log of 7 to the power of 2/3 x, and that's equal to log base 40. Okay, now I'm going to ask you to use the power rule and take this and bring it down. Not power rule, but power law. So 2/3 x times log 7 is equal to log 40. 2/3 of x times log 7. Well, once again here, I want you to understand that the 2/3 and logs are just numbers, so I can just group them together if you want. 2/3 of a log 7, and that equals to log 40. And ultimately, solving for x now, I'm going to ask you to just take log 40 and divide that by 2/3 log of 7. Okay? Calculator time. So just go ahead, take log 40, divide that by bracket 2/3 of log 7. And then close the bracket. And then press enter. And there's your answer. So x is approximately 2.84. Alright, so let's try part B. Part B is a little bit different because I guess there's a number in front of that exponent. But remember, when you're solving equations, you want to isolate x. And I think what you want to do for the first part in part B is try to isolate the exponent. So I'm going to ask you to first step to, yes, divide both sides by 3. So 2 to the power x is the same thing as 52 now, divided by 3. And then now you can convert this into logarithmic form. So we'll take log on both sides. Log 52 over 3. Once again, when you do that, I'm going to ask you to use the power law, bring that exponent down to the front, so that's x times log of 2. And this equals to log of 52 over 3. And then once again, solving for x, I'm just going to have you go x equals to log, and this is 52 over 3. I'm going to divide that by log of 2. And once again, go back to the calculator to solve this. Back to your calculator, log 52 divided by 3. And divide that by log of 2. And ba-bam, there's your answer, 4.12. And by the way, you can always double check if this is correct by then just plugging this value of x back into the original equation. So 3 times bracket 2 to the power of x, which is my answer. And let's see if that equals to 52. Oh yeah, it does. So life's good. It works. You can always check your answers, right? Uh-oh. Baby doesn't like it. You okay, baby? You don't like decimals? Yeah, most of my students doesn't like decimals either. I understand. Okay. Alright, let's turn the page. I've got 2 more for you to try. So, same kind of ideas here, everybody. So, nothing too much that's new. I will let you try it on your own then. And let's see if you can get the same answer as I do. Okay? Try on your own, please. Distribute. Now once again, I want to group all the things with x on one side. So I'm going to take that x log 2, move to the side. I know usually I put the logs in front. Doesn't really make a difference. Okay? It's multiplication, right? Once I have x's on one side, I'm going to factor out the x so I can have the number by itself. So that's log 5 minus log 2. And that's log 2 on this side. And of course, we want to solve for x. I will do that by taking log of 2 divided by log 5 minus log 2. Excuse me. And now it's time to use the calculator. There's log 2 divided by, and I put a bracket around the denominator again because I have so many different things that are going on. Log 5, take away log 2. Carefully the brackets, not like me last time making a mistake. Close it, and there you have it, 0.76. Okay. D is very similar to the one we just did in C and our first example today. So once again, I don't want to do it for you. Why don't you go ahead and try it on your own. Please stop the video and do it on your own first. And let's see if you get the same answer as me. Okay? Go. Mm-hmm. Okay. You can't see. Alright. Maybe you can't see. Now she can see. So once again, I'm grouping all the x's, grouping all the numbers. I'm going to factor out the x. Mm-hmm. Okay. No, you don't like logarithms. Baby doesn't like logarithms. How can that be? Alright. You're almost done. Almost done. Just go to your calculator now. Right? And plug things in. Are you hungry, baby? Daddy's gonna get you some food, I guess, eh? Alright. 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 Mm-hmm. Mm-hmm. Okay. Alright, ladies and gents, 3.44 is the answer. Hope you got that. Now, just a quick thing here before I leave this example. I want you to focus on this nasty beast here. Some of you are like, hey, Mr. Lee, that's too many things, and maybe I could apply some rules. Mm-hmm. If you want to apply some rules, you can. What you'll see is that the numerator is subtraction, so some people will write that as division. That's perfectly fine. And then, oh, remember those 3's in front and the 2's in front? Well, I can rewrite the bottom as just exponents, so that's log 2 cubed minus log, and that's 3 squared, right? I bring the 2 up front, or up to the top. So this is the same thing as log 2 thirds, and then I can rewrite the bottom. 2 cubed is just 8, and then 3 squared is just 9. So if you type this into your calculator, it's perfectly fine as well. Log 2 thirds, okay, divide by log 8 ninths. That works too. You'll get the same thing. All right. Doesn't matter what you want to do. Some extra steps using the laws, which is perfectly fine. But when you're solving, you might be thinking to yourself, "What a waste of time." Fair enough. Okay. All right. So now I'm going to ask you to apply these same principles that you solved using these exponential equations to the word problems that we did before. So remember that stuff we did before with cell population, how it doubles every hour or something like that? Yeah, here's another example of that. So cell population doubles every 5 hours. And the question is, how long will it take 4 cells to reach a count of 16,384? So, don't know if you remember the general form of the equation. Y equals to A, some initial amount, some C, which is some sort of rate, and then, of course, X over T. So in this case here, we have 4 cells, so we're starting with 4 cells. And then the rate here is, it doubles, so there you go. C is 2. But it doubles every 5 hours, so I'm going to go X divided by 5. And that gives me my Y value, which is my ending amount. In this case, my ending amount, I know, it's 16,384. So that's equals to 4 times 2 to the power of x over 5. And now we have a nice, lovely exponential equation that I'm going to ask you now to solve. Yeah. Yes, you can solve it too. Maybe you can do it too. So, how do we do this? Well, I'm going to ask you to try to isolate the exponents. So let's divide both sides by 4 first of all. Fun, isn't it? 16,384 divided by 4. That gives you 4,096. That equals 2 to the power of x over 5. And then now to solve, I'm going to ask you to take log on both sides. So just log of 4096 equals log of 2 to the power of x over 5. The log 4096 stays the same. But I can bring down my x over 5. In this case, I'm actually going to solve for x over 5 first, just because I think it's a little bit nicer. So let's just take log 4096. Ooh, yeah, log 2. And that equals x over 5. I'm going to evaluate this part first. Alright, Yan Yan. We will finish this off very quickly. Okay, 4096 divided by log 2. Hey, that's 12. So that's 12. What's x? 12 times 5? 60. Okay? So, how long will it take? About 60 hours. Alright, so I'd like you to try example number 3 now. Something similar that we've done before, you bet, because it's half-life again. So, the hardest part usually with these questions is once again setting up the equation. But I've given you that general format. I like this y equals to a c to the power of x over t. That's what I like. We've got this thing called carbon-14. It has a half-life of 5,760 years. I'd like you to go ahead and find the age of the specimen with 24% of carbon-14 relative to the living matter, meaning my final amount must be 24%. And if I start it with 100%, that makes total sense. Since the half-life is half, my rate must be 1/2. And we're going x over 5760. Let's go ahead and try to solve this now. We're going to divide both sides by 100, so we get 0.24 equals to 1/2 to the power of x over 5760. And remember, in the past, what we had to do was kind of guess and test, or we used the graphing calculator. But now we can just take log on both sides. So log of 0.24 equals x over 5760 of log of 1/2. I like to just put all the logs to one side this time first of all. So let's go log 0.24 divided by log 0.5. And that equals to x over 5760. Calculator time. We'll do log of 0.24. Divide that by log of 0.5. We'll get this fabulous number of 2.05 blah 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 blah. So I'll write it down. 2.05 blah 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 blah. And that equals to x over 5,760. So I guess to solve for x, we want to multiply both sides by 5,760. So 5760 times the 2.05 blah 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 blah. And what does that equal to? See, I kept that number in my calculator. So 5760. Let's multiply it by that. Whoa, lots of years. 11,859.2. And I guess this would be years. So, it's been living for a long, long time. Okay. By the way, if you hear that background music, that's a little baby girl playing with her little toy. Yes, I guess she got bored of math. How can that be? Alright, turn the page. We've got one last page for you. Another question that you've seen before, this investment type of question. Whenever you're trying to solve for the exponent, as this will be the case, well, look no further than to just use logs now. Don't worry about using the graphing calculator. Don't worry about changing them into an exponential form. Just go ahead and use logs. Now, once again, I've got $1,200 and I want to invest it and earn, I guess it's 8,000 here, so I can take a trip to Europe with my family. Yay, yay, yay. $8,000. That's a pretty cheap trip. Oh well, whatever. I'm cheap. So the question is, if he invests the money into account with an annual percentage rate of 8%, compounded monthly, the question here is, how long will it take Mr. Lee's investment to grow so that he can afford his trip? Now, just to make the numbers a little bit nicer, I'm going to ask you to make a change here. So instead of 8%, I want you to make this 9%. Just a little bit easier on the calculator, okay? Alright, so 9%. All right, remember that formula? A equals to, I think, the principal times 1 plus the interest rate as a decimal, divided by n, where n is the number of compounding periods, times n, or sorry, not times, but to the power of n times t. So once again here, A stands for the final amount, which is 8,000. P stands for the initial amount, which is, I guess, 1,200. I got 1 plus I, and this is 0.09. And because there are 12 months in a year, and I'm compounding monthly, n is 12, and this becomes the power of 12t. Now you know why I chose 0.09, because if I were to use the calculator here, 0.09 divided by 12, that's a nice number. Yeah, see? 8,000, I'm going to have to divide that by 1,200. Might not be such a nice number. Nope, but that's okay. So that's 6 2/3, I guess. I'll change it to a fraction. So to simplify here, we've got 20 over 3. And then this becomes 1.0075 raised to the power of 12t. And of course here, to solve, once again, you're going to take log on both sides. So I'm going to go log of the 20 over 3. And if I take log here, I'm going to skip a step. I'm going to move down to 12t. And I'll have a log 1.0075. I'm going to solve for t here, so I'm going to isolate that. How about dividing both sides by log? So I'm going to divide both sides by the log 1.0075. That equals to 12t. Let's figure out what that is. Let's see, log 20 divided by 3. I'm going to take that and divide by log 1.0075. Oops, 1.0075, 0075. And then, what do we have here? Wow. 253.9. 253.9 is the same thing as 12t. I want to solve for t, so we're going to divide both sides by 12. And when we do that, how about a whopping 21.2 years? Yikes. 21.2 years is how long I'll have to wait in order if I have enough money to go to Europe with my family. I think in 21.2 years, that $8,000 won't be enough for the whole trip. That might just be enough for the plane ticket. Who knows? I guess I can always dream. But wait! What if I decide to do something differently? Instead of just taking one lump sum of $1,200 and sticking it in to an account and letting it grow by itself, what if I decided to actually invest $100 each month instead of $1,200 that 1 year? Okay, I know I'm going to do this more often because I'm thinking I can save up $100 every single month. Okay, so what happens if I do this now? I'm going to invest $100 at the end of each month. Okay, so think about this number line here. So this is like the number line, not the number line, the timeline, I guess. That's 0. Here's 1 year. Here's 2 years, and so on. Now I'm going to put in $100 every month. So January, February, March, April, May, June, July, August, September, October, November, and December. Okay, 12 payments. And I'm going to continue to do this every single year. Okay, so $100 every single time. Okay, if I keep doing that, the question is, how long will it take for him to save up enough money for this trip? Okay, hold on. Baby's crying. Baby's okay. Now, in this case, I can use this formula. Now, this formula is kind of weird because it just came out of nowhere. I'll prove it to you after this. This will be an extra thing. Okay, but if you don't care about the proof, let me just use the formula and let's see how that logarithms come in handy when you do this one. Notice that FV stands for the future value, meaning how much money do you want at the end in the future. Okay, and in this case, I want enough money to save enough for the trip. That'd be $8,000. And then N is the number of what they call equal periodic payments. So that's how many times I'm going to put in $100. Okay. R, of course, is the amount. That's the $100 that I put in every single month. And I is the interest rate per compounding period. So this is the key part. It's per compounding period. So let's deal with that first. Since I is 7.5% this time, and its compounding period is, I guess I'm doing this every month, it's 12, I want you to change that to 0.075. You're going to have to divide that by 12. Okay, so let's do that here. 0.075 divided by 12. So what you're in essence getting interest every single month is less than 1%. It's 0.00625. Okay, that's the interest you're getting every single month. So now, since you have all these pieces of information, you can just use the formula and calculate. Okay, so your future value, once again, is $8,000. That's what I want in the future. Your R is your amount of payments every single month, which is 100. 1 plus I, which is 0.00625, raised to the power of n, which we don't know, and then minus 1, in a bigger bracket, all over I, 0.00625. Okay. So let's see if I can simplify this a little bit. Trying to isolate the power stuff. So I think I'm going to get rid of this 0.00625. So that'll be 8,000 times 0.00625. And why don't I divide that by the 100 as well while I'm at it? And that leaves us with the 1.00625 to the power n minus 1. Let's just do some calculations here. 8,000 times 0.00625 divided by 100. That's, 0.5. Lovely. 0.5. 1.00625 power n minus 1. Guess I should add 1 to both sides now. So now I have 1.5 equals to 1.00625 to the power n. And lo and behold, a nice, lovely exponential equation that you can now solve by taking logarithms. Log 1.5. Once again, let's skip a step. N times log. That's times, by the way. 1.00625. Going to solve for n by just taking the log 1.5, dividing by log of 1.00625, and ba-bam! I look forward to getting my final answer. Log 1.5 divided by log 1.00625. 65. Okay. Now n is 65. It's not 65 years though. Okay. This is the number of periods. So n equals 65 periods, or I'm going to have to do 65 of these $100 payments. Well, think about it. 65 $100 payments. I'm making these payments every month. So really, if I'm asking for how long it's going to take, I should take 65 divided by 12, and that will tell me how many years it's going to take me to save up enough money. So, it's not too bad. Only about 5 and I guess 5.416667 years. If I want to be even more accurate, I'm just going to figure out how many months that is, subtract off the 5, multiply that by 12. Looks like it's, 5 years and 5 months. Much, much quicker than in part A, where it took me 21 years. But you see the difference in these two questions? The difference is, in part B, you're investing $100 every single month, okay? Just $100 every month. If you can actually think about this, okay, you guys, when you're working, if you can store away $100 every month, look what's going to happen to you. In 5 years, you could actually have $8,000. Okay, I'm done for 8.4, but for those of you who want to stay behind to take a look at how we can figure out or derive that formula for future value, then keep on listening. All right. Let's see. Let's take a new page. Okay, future value. How did that future value formula come to be? Let me write that down once again for you. FV, future value, equals R, bracket, 1 plus I to the power n minus 1 all over I. Okay. Now remember once again, what are we doing here? On our timeline, this is t equals to 0. You are saying, let's say this is 1, this is 2, and so on. You're saying you're putting in these monthly payments, or doesn't have to be monthly, just payments, regular payments. These are your R's. And you're doing this for an extended period of time until sometime at the end. Okay, so let's call this Tn. Okay, so you're doing this, put in, dot, 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 until time n. This is like your final time, right? So think about what's going on in terms of the interest you're gaining for each of these pieces of R. Remember, your interest that you're earning is 1 plus I for each of these periods. So looking at this first R, which I'm going to call R1, okay? I guess I'm earning interest here, and then here, and here, and here, and here, and here. So your amount grows. Your, I guess, accumulated amount, okay, your accumulated amount. Oh, hold on, phone call. Okay, so your accumulated amount then just becomes this R1 payment, and you're going to multiply that by 1 plus I every single time. How many times are you doing this? Well, I guess you're doing this n times. And then if you're looking at your next payment here, I'll call this the, I guess, R2. It's the same idea. It's the same amount, right? So the accumulated amount will be whatever that R2 is. But then notice I'm going to multiply by 1 plus I, but not to the power n. It's not doing this n times, but I'm going to do it 1 less. So it's n minus 1. Okay? And the third one will be, I guess, R3, 1 plus I, and it'd be n minus 2, and so on and so forth until this last kind of payment. Don't really know what it is. Okay. Here's your R, I guess, n minus 1, like the second to the last one. 1 plus I with just one payment, and then the last one, right at that moment in time, well, there's no interest earned on that. So what you're doing is you're collecting all these things together. Okay, now I shouldn't have changed it to R1, R2, R3 because they're actually all the same amount, right? So they're really just the exact amount. Like in the previous example, is $100. So let's just keep it as R. But I want to use the 1, 2, 3 to show you which payment it is. So look what we've got now. We've got R bracket 1 plus I to the power n plus R 1 plus I to the power n minus 1 plus R 1 plus I n minus 2, and so on and so on and so forth. R 1 plus I plus R. Well, notice there's R involved, so I'm going to factor out the R. Actually, I don't even have to do that if you don't want to, but okay, let's just leave it like this for now. Okay. Anyone kind of see what type of sequence this is? Think back to good old grade 11 stuff. See how I start with R over here on the right, and then I'm multiplying by a 1 plus I, and keep doing that and doing that and doing that. Since it's multiplicative, this is a geometric, and because it's adding them all together, it's a geometric series. And remember the formula for calculating the sum of a geometric series? That's the A value, the initial value. I think it's, what do we have here? R to the power n minus 1 over R minus 1. R, of course, stands for the common ratio. So look at here, our first term, our initial term, is R. So A is just equal to R. The little r is our common ratio. It's the 1 plus I to the power of n. minus 1. And the denominator r is just 1 plus I minus 1. So what do we have here? We've got r 1 plus I to the power of n minus 1. And then the denominator just simplifies to r. And that's the sum. And the sum just means our future value, the total of all the accumulated payments.